In this lesson, we're going to learn about the Bohr model, which is kind of a continuation of the atomic emission spectra that we learned about previously. So, first of all, a little quick background about Niels Bohr. He's a Danish scientist and is actually a colleague of Ernest Rutherford, which you remember he helped us figure out that the nucleus was a part of the atom. But one thing that he worked on specifically was looking at hydrogen, especially the atomic emission spectrum of hydrogen, and looking at each spectral line. So what that means basically is all those individual colors that come out of the atomic emission spectrum of hydrogen, right? He basically was trying to analyze those and make some conclusions about maybe how the electrons are arranged there. So each line, right, each individual color, whether it be red or blue or green, corresponds to a very specific relaxation of an electron from a higher energy level to a lower energy level. And that's kind of what we referred to earlier on. If you remember, there's those diagrams where we talked about the electrons going up and going down. That's effectively what we're saying, is that he was able to put that together based on his own analysis. So the Bohr model here, again, is kind of the next step. So the Rutherford model of the atom, if you remember, pretty much just had a nucleus, and then you had some floating around, electrons that were just floating around, but now we're actually going to try and organize it. So this is the first time we're going to see a good organization based on experimental data. So let's go and take a look here again. This diagram right here on the right effectively shows you what we're looking at. So if you look here, right, this is effectively these rings right here. Each of these represents the energy level. So again, on the previous diagram, we had just seen something look like this. There's individual lines and such. And then you kind of have the electrons going from here to here, going from here to here, sometimes going down. So, but if you kind of took these and expanded it and kind of made it into a circle, right? Each of these energy levels basically corresponds to one of those rings, or vice versa. Each of those rings corresponds to an energy level. And so the electrons would hang out here, or they can hang out here, or they hang out here, but of course, never in between, right? Never on these areas in between these lines, because once again, we're finding out that this stuff is quantized, right? These energy levels are quantized. There's no in between. And what they're saying again is that right here on the bottom is a line spectrum, right? So this effectively is the same thing as the atomic emission spectrum, right? And you see the individual lines appear. Well, again, these lines all are these colors anyway, appear because there's a very specific pattern of an electron going from this energy level, in this case from n equals 5, all the way down to the n equals 2 energy level. Or that the energy level goes from, or so the electron is going to go from n equals 3 all the way down to n equals 2, and that generates this color. And remember, the bigger the drop in energy, right, the different color, the color comes out of it, because it's based on that energy is there. So this color comes out because that's the energy difference between these two lines. And he made these calculations based on these colors. Don't forget, right, that you can make these calculations happen when you look at the color of a light, right? You can figure out its corresponding frequency, which you can then, kind of relate to its energy. So based on these calculations, again, this is a very, very small part of the overall system that he used to figure out that, again, these effectively are the energy levels. And going back over here, so based on these calculations, he concluded that electrons orbit the nucleus on fixed circular paths, on these orbits. And what we're saying here is that they're fixed, right? Meaning they can't expand, they're not going to contract, they're effectively just set in place, and that these electrons are going to sort of circle the nucleus as if they're like, planets around the sun or something. And this diagram on the left here basically is just kind of a smaller version of what we described here. These electrons, of course, coming in and out, getting big and small, or at least going from bigger to smaller energy levels and rings, and as such, there's different corresponding energies associated with it. So this effectively is the basis behind the Bohr model. Let's kind of bring that back to what we have learned already. First of all, electrons only able to travel along orbits at fixed distances from the nucleus and nothing in between. What concept, with what concept is consistent? And that's consistent with this idea of quanta, right? Quantization. That these electrons are quantized, or these energy levels, these energy levels are quantized so that you can't have energy levels that are between other energy levels, right? There's no like in-between spaces that these electrons can orbit. They have to orbit exactly on those energy levels. The concept of the energy level was discussed earlier. How is it included in the Bohr model? Well, the energy level, right, from the simple diagram that we saw when we talked about the atomic emission spectrum, Well, that again has those same patterns appear in the Bohr model as the actual rings themselves, as the actual orbits themselves. Right? So this is the path that those electrons float around on. And then finally, how do the light and spectral lines emitted from hydrogen gas provide what information about orbits around the nucleus? So basically, whatever colors we see, right, the colors correspond to an energy. Right? You can calculate the energy that a light has. And then, based on the energy, he was able to figure out the distance between the orbits. Right? So in a very, very sloppy handwriting there, is that the colors, again, correspond to a specific energy. Again, we know how to do those calculations, right? We can figure out the frequency of a light and then figure out how much energy that light possesses. And then based on that energy, he could then reason and figure out what those orbits sizes are and how far apart these orbits are to each other, right? So kind of going back up here, he can figure out that distance from here to here because he can make calculations based on the energy of the light that's emitted. Now, this right here in the next slide is something called the spectral series. This again is not an overly important part of what we're learning, but basically he was able to then or other scientists were able to take this framework and then find that really there's a certain pattern that occurs every time electrons relax to a certain level. So first of all, let's go and take a look at this pattern here. First of all, this is a plus little sphere there. That's basically representing the one proton of a hydrogen atom. And then you see that you have the n equals 1 ring, like this, the n equals 2 ring around it, the n equals 3 ring, 4, 5, 6, 7. So basically they're being labeled, right? That's the first energy level, the second energy level, third energy level, so on and so forth. And you can see that there's like kind of 3 main patterns here. You have this one, the ultraviolet series, the Lyman series, the infrared series, and then the visible series. And basically what they're saying, or what this diagram is showing, is that if an electron starts off wherever it's going to start off, but it ends at the n equals 1, it's going to be some form of ultraviolet radiation, right? So the electron, when it relaxes down to the n equals 1, it's going to release some form of ultraviolet light. So it doesn't matter if it starts from n7, n equals 6, n equals 5. It's going to, if it relaxes down at n equals 1 directly, it's going to release ultraviolet. Whereas, if you have a series right here that ends at n equals 2, right? So if an electron comes from here, right, n equals something, and then ends at, and relaxes down to n equals 2, it's going to release some sort of a visible light. And then finally, if you have an electron that relaxes down to n equals 3, regardless of where it starts, it's going to release some sort of infrared light. And that should make sense, right? Because landing at n equals 1 all the way down there, that's usually going to be a lot more energy than something that ends at n equals 2 or n equals 3. So that means the ultraviolet series, right, which is the highest energy kind of light on this diagram, is going to have correspond to the biggest release of energy and the biggest relaxation, compared to something that only relaxes down to n equals 3, which is a lot less energy that's going to be released. Therefore, you have a less energetic light that comes out from it. A couple of features and shortcomings of the Bohr model. First of all, it is the first widely accepted attempt at understanding the arrangement of electrons, right? So at the time, there are many people coming up with many different kinds of electron arrangements, but this one seemed to be the first that held a lot of water in the scientific community, based on the systematic approach that Bohr took to understanding electrons. It's also a really good basic visual for explaining electrons and also understanding it, right? But you'll find that, in fact, the Bohr model ends up being wrong, right? So the Bohr model ends up not being wholly accurate. But it still holds a lot of importance because it really does give us a good framework for understanding the next step. And also, we use the Bohr model a lot in explaining a lot of simpler atoms, which again you see here in the next line. However, right, this is kind of the con part, or the shortcomings, accounted for emission spectrum for hydrogen, but not really a whole lot else, right? So hydrogen is one of however many elements that exist. And so this atomic emission spectrum actually, for hydrogen only was accurate so for the Bohr model that he created. So that Bohr model really couldn't be extrapolated. The same idea couldn't be extrapolated to, say, helium or nitrogen, right? Because their pattern of excitation relaxation is very different. Also didn't really address how the positive nucleus and the negative electrons don't just collide, right? Because aren't they positive, negative, oppositely charged things? Don't they just kind of run into each other? So this doesn't explain how the electrons, even though they're now organized, at least according to his model, didn't really just kind of collide and crash into the nucleus. And then finally, it didn't really address chemical reactivity, right? So even though you have electrons being arranged in a certain way, the pattern didn't really help us understand why certain things bonded to other atoms, right? So why one set of electrons will be transferred or whatnot in certain bonding patterns. So let's talk really quickly about how Bohr models are interpreted and how to draw them yourself. First of all, the nucleus can just be sort of assumed as a certain number of protons and neutrons. You can just kind of say P equals blank, N equals blank for the nucleus. So the P, of course, the number of protons, that corresponds to the atomic number on the periodic table. And then N, the number of neutrons, that's actually going to correspond to the mass number that's given to you, right? So remember, you can't get the number of the number of neutrons unless you have a mass number that's given to you. We'll talk about that in a little bit. Then each orbit, so each ring, effectively is an energy level, which we discussed before. And it's represented by the N equals blank. So this is also a little confusing because these two N's refer to different things. This N's, again, the nucleus, that refers to the neutrons. This N equals to something that's actually referring to the rings themselves, so the actual orbits themselves. So the first energy level is given the label N equals 1. The second energy level is given N equals 2, N equals 3, so on and so forth. And each energy level can hold a maximum of 2n squared electrons. So the first ring, therefore the first energy level, can hold a maximum of 2 electrons, right? Because when you have n that equals to 1 squared, and then times 2, that's equal to 2. The second energy level can hold a maximum of 8 electrons, right? Because the second energy level, if I put 2 in here, 2 squared is 4, 4 times 2 is 8. Makes sense. The third energy level can hold a maximum of blank electrons, right? So let's try this again. 3 squared is 9 times 2, which will be 18. All right. And of course, that pattern goes on. If I make n equals 4, that becomes 32, so on and so forth. So how do you draw this? First of all, you got to figure out the number of protons, neutrons, and electrons. The protons and neutrons, of course, require the mass number. Number of electrons, of course, that then corresponds to the number of protons because, right, they're oppositely charged, and we're talking about neutral atoms. So that means whatever number of protons you have will also be the number of electrons that you have to assign. You're going to sketch a nucleus with the appropriate number of protons and neutrons, P equals N equals. And you're going to draw the appropriate number of orbits and assign all the electrons starting with N equals 1. Of course, electrons should be drawn on the orbit, and you can denote them as dots or the E minus symbol, which I'll show you on the next slide. All right. So the Bohr model for each of the following isotopes is going to do hydrogen 1. So we'll do this up here. Hydrogen 1 has 1 proton and 0 neutrons. And since it only has 1 electron we need to assign, that means we just have 1 ring, and that's it. If you want to label it of N equals 1, right, saying that this is the first energy level, you're welcome to do it, but that's not required. All right, what about aluminum 25, right? So finding aluminum on the periodic table, so you'll see that, I'll do this over here, number of protons in aluminum is 13. And because we have a mass number of 25, we know that the difference between 13 and 25 is going to be 12. So we have 12 neutrons. We also have 13 electrons to assign. Let's go ahead and make that happen. Here and here. Now, let's start off with these two. We have 13 electrons to assign, so let's go ahead and assign 2 here. We'll do this, and we'll do this. Right. I like to pair them up just because it's easier to count. And then we have 11 more electrons to assign. On this one, right, this is the N equals 2. I know I can hold a maximum of 8 electrons. Right? Remember the 2n squared relationship that we talked about before. Second energy level, so you can hold a max of 8. So at this time we have assigned a total of 10. We have 3 more to go, and go ahead and assign on the third one. This third one can hold a max of 18. So we know those 3 fall well within that 18. All right, fluorine 18. Let's try this one. Fluorine 18. This one, let's do this in green. The fluorine 18 is going to be where we have 9 protons because it has an atomic number of 9, 9 neutrons, and that means we have to assign 9 electrons. So how's that going to look? Well, again, this first ring, I can hold a maximum of 2. The first energy level, 2n squared. Second energy level, I can hold a maximum of 8. So I have 7 left to assign, right? I've assigned 2 of the 9, so I have 7 left to assign. That's going to be 1, 2, 3, 4, 5, 6, and 7. And that takes care of fluorine 18. I'll let you try carbon 14, right? Kind of following the same pattern here, identifying the nucleus and then assigning the right number of electrons. All right, that'll do it.